Hi, I'm Dr. Nijisha Shajal, Assistant Professor from the Department of Biomedical Engineering, SRM Institute of Science and Technology, Kattangalattur. In the course Principles of Medical Imaging, we are going to see Unit 2, Computer Tomography. So in this particular session, we'll be discussing computer tomography, the basic principles, the contrast scale, CT numbers, and just we'll start with an introduction of the CT system components and the scanning system. Let's start the session. So computer tomography. So what do you mean by computer tomography? Before that, we need to understand what are the limitations of X-rays. So if you see X-rays, we are sending X-rays from the top and you're taking the images at the bottom. So what happens? It is passing through different layers of tissue and you're getting to know if there is any obstructing something that is obstructing the X-rays, then you get to see that in the output. So if you see whatever the region that it is crossing, no, it is getting superimposed. The 3D information is getting superimposed into a single plane. So what happens? Diagnosis becomes confusing and difficult. The second important limitation is that the only which are objects which are having high variations in density. You would have seen the tissue, the bone, like that only those can be visualized in X-rays. Tissue, what about different types of tissue, their blood vessels, the normal tissue, fat, all those you cannot see the difference. So because of this, what happens is it becomes difficult to discern the shape and the composition of soft tissue organs. So it is overall the brain, everything, it becomes very, very tough. Brain cannot be imaged because when you're sending the X-rays, the skull attenuates the X-rays. Totally the brain you're going to not, you will not be able to image. Only the heart part, only the heart tissues you can image. The bony structure. So the solution to this was invented and developed by G. N. Hounsfield at the Center Research Laboratory of EMI Limited, UK, and that is how computer tomography came into existence. Before we go to that, what do you mean by tomography? So it has two words, tomo and something called as graphy. Tomo is nothing but a slice or a section. That is what we call it as tomo. So in this case, you're going to image a section, a slice of a body. That's all. So this was developed to reduce the superimposition principle and using the that is with the which was superimposition principle, which was the effect of the simple radiography. How do you do that? You're going to have a different type of arrangement. You're going to use an X-ray tube. You're going to have a film. Both are the same, except that you're going to move both of them synchronously. So from one, if you have, imagine one slice, you're going to have the X-ray, the photographic film, but you're going to move this synchronously throughout the slice. So that in one plane of the image, no, you at a point you're going to take a section of the patient, and that you're going to view it in all the directions, the whole 360-degree you're going to do, and you're going to blur the other sections. So in this case, you're going to view the X-ray imaging from different angles, and how you can get it back. So you're going to send X-rays, you're going to get it, but you're going to use mathematical reconstructions. Not simple, like we say, you have multiple X-rays, you're going to combine all of them. You're going to use reconstruction technique to reverse it and to find out how the X-rays are, and then you're going to create the image. You're going to reconstruct the image on a video monitor. So CT, they can distinguish between different types of brain tissues, normal, coagulated blood, everything can be easily seen. So this soft tissues also can be easily visualized with the help of CT. The only disadvantage is that you're going to use X-rays for viewing it. Here you can see you have the normal bones as well as the CT images. So if you see here, the bony structures are also observed, but soft tissues are also imaged in that. All different types of soft tissue. The brain can be imaged, the spinal cord, everything can be imaged in the CT image. This is the axial plane. So based on what plane you're going to view, the X-rays are going to be sent. So in the axial plane, the X-rays will be sent accordingly. So the X-rays and the, tube, no, X-ray tube and the detector will rotate around, and you use different type of mathematical reconstruction algorithm and you image it back. This is how a CT machine looks like. It is in like a donut shape. Why? Because your tube and the detector has to rotate around and then you have a console outside where you're going to get the images, then you're going to reconstruct it and you're going to see it in the computer. So it's full and full digital only. There is no something like a film developing, no concept like that. To understand how it goes, let us see the basic principles of the CT. Computer tomography, like we saw, it differs from the conventional X-ray, how we are going to reconstruct from a large number of absorption profiles which are taken at regular angular intervals around the slice. So you have the absorption profile, you're going to take the absorption profile like that throughout the slide, different angles, then you're going to find out the image. Okay. So here if you see, you're going to use a finely collimated source. So the source, X-ray source will be small, the detector will be small, and you're going to detect it throughout. Okay. For directions along which path length that through the tissue is longer, fewer X-rays are transmitted as compared to the directions where the tissue, where there are lesser tissues attenuating the X-rays. This is the same concept. So imagine you have a tissue, like imagine you have a profile. If you have denser tissue, naturally the X-rays which are coming out going to be lesser. In the other side, it is going to be easier for it to come out. Now, in principle, CT involves the determination of attenuation characteristics for each small volume of the tissue in the patient's slice. Now, this is constituting nothing but the transmitted radiation intensity recorded from the various irradiation directions. Now, it is these calculated tissue attenuation characteristics that you are going to compose the CT image. So, to understand this, we need to know few concepts, okay. So, for that, I need to know what do you mean by the incident radiation, how much you are getting transmitted, all that. So, for this, you have a formula which is nothing but IT, that is the transmitted light is equal to the incident light into e power minus nu into x. Nu is nothing but the characteristics attenuation coefficient of the tissue, and x is the thickness of the tissue. So imagine I have a block, I'm going to send incident light. How much is the light that is going to come out? It depends upon the thickness, what is the distance that it has to travel. It depends on the density, that is nothing but the characteristic attenuation coefficient of the tissue, and it depends on the incident light. Now what you're going to do, one slice if you have, you're going to divide the slice into small units which are called as voxels. Each voxel will have its own attenuation coefficient, correct? Each and everything will have different densities. Now imagine you have a continuous line of voxels. You're sending, it is nothing but the total will be nothing but the addition, the sum of the voxel attenuation coefficients of each X-ray beam direction. Naturally, it is going to be added. So what happens at the end? When you add everything, individual values you don't get to know. So in order for us to find out individual this, you're going to measure from different direction. That is the only concept. Okay. So CET uses the knowledge of the attenuation coefficient sums which are derived from X-ray intensity measurements made at all the various irradiation directions. However, for what? To calculate the attenuation coefficients of each individual voxels to form the CT image. Now let us consider this is your slice. Okay, some slice you want to image. Now I'm going to divide this into pieces, and this each piece is called as a voxel. Now if you see, each voxel will have different attenuation coefficient, in other words density. Now imagine you have S, which is nothing but a tumor. Okay. Now when I send a light, when I send an X-ray from here to here, what will be the output here? It will be the sum of all of these, correct? So imagine this is 0, 0, 0. This will be 10, 0, 0, 0 like that. So what will be the output I get? 10 I get. Now imagine I'm changing this direction. Again I'm taking. At this point what will happen? It will be the sum of this, which is 0, 0, 10 like that. So when I add this and this, it will be 10, 10. Now imagine I am going to change the direction. I'm going to send in this way. What is the sum here? Here it is going to be 0. So at what, like this, when I do around, at one point I will be able to trace and tell at each and every voxel what is my attenuation coefficient. In other words, I'm getting a 360-degree view of the internal part of the slice. That is the concept of CT. Okay. So for to view this, this is how a CT machine is set up. So you have something called as a gantry, which is nothing but your donut shape. So in the gantry, you have a hole, because in the top you have the X-ray tube, you have a detector. So top bottom means it keeps rotating. So at one point, at one place you have the X-ray tube, the other place you have the detector. The X-ray tube is going to give the X-rays. These X-rays are going to be very, very fine pinpoint hole, because it's going to be very small area, so that I can pinpointly it falls into the patient, and I'm going to use the detector for detecting it. Now what happens is, at this point, all the addition, whatever we saw here is going to attenuation coefficients output is going to take, and you're going to see it. Now what, like this, it keeps rotating, you keep rotating into such a way that this full slice you're going to pick it up. So the main thing you have to understand is that this whole system has to move, and if I want to scan different areas, the patient has to move. So this is how it is done. And here they just want to show that you lie down, and then your patient is raised up in the patient table, and you send it exactly in the center part of the cantu. Again, to understand this better, so this is the subject, you're going to scan this part, the axial part I'm going to scan. In that case, I'm going to use the X-ray tube. The X-ray tube is, you have, remember in the previous unit, we studied about the collimator. It's going to shape it and send it as a fine beam. And you're going to send the X-ray. In the opposite side, you're going to use a collimator again to allow collimator, or it's called as a grid, to allow only single rays, the direct, to avoid all this scattered radiation, and allow only the single rays to come to the detector. Now the detector will detect it. Now this both will rotate around in such a way that you measure this, and you have a computer which picks up, detects it, and then you use reconstruction algorithm, and you view it as a one. This keeps rotating, it gets calculated, and it comes out as a slice of the image. So this is the basic principle of your CT. So in order to understand how you have this attenuation coefficients, from the attenuation coefficients, how the contrast is being calculated, I need to know something called as a contrast scale, because all at the end I'm getting is attenuation coefficient intensity. That I need to convert it as an image, a black and white image. For that I need to know what do you mean by contrast scale. So the linear attenuation coefficient of the tissue is represented by the scanner, and it usually consists of a value of -1000 to 1000. So the whatever is the value that you get, you're going to normalize it to -1000 to 1000. So this value is being given as the Hounsfield unit based on the inventor of the CT. So it is written as H, and this is called as a CT number. So whatever attenuation coefficients you have, that is all normalized to -1000 to 1000. The relationship between the linear attenuation, to understand how they are related, this is the formula. So 1 Hounsfield unit is equal to nu minus nu of water divided by water into 1000, which means that attenuation coefficient of the water is a base. So any material you have, that minus the attenuation coefficient of water by water into 100, the attenuation coefficient, this, if you converted it into some value, is called as a Hounsfield unit. So this number only you're going to represent it as a black and white image. Okay, so just remember that you have -1000 to 1000, 0 is the water. So what about -1000? -1000 is air, and +1000 is highly dense material. In case in a body, it will be naturally bone on that. Okay, so this is how to remember. So bone, you can see here. So -1000 to 1000, -1000 is air, 1000 most dense material. In between you have the water. So anything which falls in between have different Hounsfield unit. That is a CT number. So you can see kidneys right in this range, fat, breast, all this you can see. Lungs, because it is airy, it falls here. Like that, based on this value, you have the Hounsfield unit to be given. The CT number has been assigned. So when you're viewing this is -1000 to 1000, you're going to convert it into a black and white gradation. Okay, so you have a window level or the window lid. So this will allow you to increase. So if you see here are what to say, the soft tissues are all in this range. You can see from -200 to around what to say 100. So this region is been what to say, it is windowed in such a way that you maximize it and you see it as a black and white scale. That is how you are able to see it in the shades of gray. Let us see the let us now see what are the different components of a CT system. So we have seen how the principle, so the components of a CT system. So majorly if you see, there are four major components, which is the scanning system. Scanning is nothing but where you're going to send the X-ray, take in the detector, you're going to detect it and you're going to reconstruct it. So this mainly includes the source and the detector. Processing, where you're going to take the readings which have been detected into intelligible picture format. You have the viewing system, which is nothing but the where you are going to actually view it. It can be in the CCTV as an image, anyway it can be, and the storage. So the main important component, if you see, is the scanning system of the CT. So this is how it looks like, the CT system. So you have the table where the patient lies. Here is the gantry, the rotating gantry. Inside the gantry, one side you will have the X-ray tube, the other side you will have the detector. So this keeps rotating. Then you have the user interface. And this is usually isolated. This kept separately. The patient alone will go inside. You have a console outside, a very, very high processing computer, which takes up the reading and which analyzes it. So everything is done by that. So we'll just see an introduction of the scanning system. So the scanning system, the purpose is nothing but to acquire enough information to reconstruct a picture for an accurate diagnosis. So you're going to just acquire the information. It requires sufficient number of independent readings for picture reconstruction and for a good spatial resolution and density discrimination. So here, if I want a very good image of the slice, I need to take multiple projections. You call it as projections or profiles. So the readings that you say, you're taking one attenuation coefficient, the intensity, all that, they are called as a profile. Like this, you need to take multiple profiles, okay? When a plane which is parallel to the X-ray beam passes through the required section, a profile is defined as the intensity of the emergent beam plotted along the line perpendicular to the X-ray beam. So you have the beam passing, coming out, whatever is the profile that you get, that is called as your profile, whatever is the X-ray beam that comes out. This profile, it represents the plot of the total absorption along that particular parallel X-ray beam. So like this, from top to bottom unit, you get a profile. Like this, throughout you're going to do some type of reconstruction and get the image back. Okay. In practice, usually what do they do is 180-degree profiles. You have 180 such profile at 1D. So small interval, you take that much of this one and then you will construct it to get a diagnostically useful picture. This will end this session. Thank you.